This lesson is all about specific heat capacity, and it's in the topic P3 particle theory. You will also find it in the topic P1 energy, and in that topic it is a required practical. But for today's lesson we're going to learn about specific heat capacity, define what it is, have a look at examples, and have a look at how to use the equation. So before we go any further, if you have a look at this picture, and if you think back, if you've been lucky enough to go to a holiday with a nice beach on it, when you're on the beach, on the sand gets really hot, and you usually go in the water to cool off. They've both been under the same sun for the same amount of time, so they both had the same amount of heat energy. Why is it that they end up as different temperatures? So when you've had to think about that, we'll go back to it, but before we do, this is the objectives and what you need to know for today's lesson. So defining specific heat capacity, using the equation, and explaining why some substances heat up and cool down faster than others, and give examples. So let's go back to thinking about the water and the sand on the beach. So there's the sun, same amount of heat going to the water, same amount of heat being transferred to the sand. But the water, the temperature rise is shown here. And for the sand, as you can see here, it's a higher temperature rise. So water's got a smaller temperature rise, so it's cooler, and the sand has got a larger temperature rise, so it is warmer. So you put the same amount of heat into some materials, so there's two different materials there, water and sand, but the temperature rise is different. And this is all to do with the difference in the specific heat capacity of water and the specific heat capacity of sand. The water has a larger specific heat capacity than the sand, so it takes a lot more energy to heat up the water to the same temperature as the sand. So here's a definition of specific heat capacity. You might possibly have to recall this in an exam, so it's one of those definitions that you will have to learn. Now you can either pause the video here and write the notes, or use the presentation separately to make notes into your book. So the definition reads like this: the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Now I've put those two in red because people often forget to put 1 kilogram. They just say raise the temperature, and it's really important to put 1 kilogram in, and by how much? 1 degree Celsius. So make sure that you are not missing out those keywords in your definition. Now, going back to cooling curves or heating curves, this is actually a cooling curve. This part here where the red arrows are, okay, the gas there is cooling down, and here's the change of state, and then it's cooling down even more here as it's a liquid, and then here it's a change of state from liquid to solid, and then the solid will cool down to the ambient temperature, the room temperature. Now here with these red arrows here are showing the specific heat capacity, and that is represented on the slope part of the graph. Now we come on to the equation for specific heat capacity. So the word energy is equal to the mass times the specific heat capacity times the temperature change. In fact, really, it is a change in energy because you're looking at how much energy is needed to raise the temperature of the material. So this is how we write the equation. Now these triangles here, delta, are representing change. So delta E, change in energy. Sometimes you might just see it written as E. Very importantly, the unit for energy is joules, written with a capital J. Mass here for the equation is measured in kilograms, so if you're given it in grams, you change it to kilograms. C stands for the specific heat capacity, and it's a bit of a complicated unit, but if you look at it, joules per kilogram degrees Celsius, because you're looking at the amount of energy that's going in to raise 1 kilogram of the substance by 1 degree Celsius. And this unit here, delta theta, represents the temperature change measured in degrees Celsius. So, if you just remember that little delta triangle symbol, just means the change in whatever you are measuring. So here is the triangle for the equation for specific heat capacity. Now the good news is that you are given this equation in the exam. However, you still need to be able to use it, and sometimes people are put off by this bit here because you've got 3 things here to find out. 3 quantities: mass, specific heat capacity, and change in temperature. But as the same as the triangles where you only have 2 quantities here, it's exactly the same procedure. So for example, if you want to find mass, cover up mass, and then you need to divide energy by the answer to the multiplication of specific heat capacity by the temperature change. If you want to find specific heat capacity, you multiply mass by temperature change, and then the energy, there you will have that value in the equation. Divide this answer into the energy. And just remember your units for specific heat capacity. Again, a little bit tricky, but it's joules per kilograms degrees Celsius. This slide shows a worked example. So it tells you here water has a specific heat capacity of 4,200. Now you're not expected to learn these. You will be given it, or you may be asked to work it out, and you'll be given all the other information in the equation. It might be an idea, I think, to try and remember the specific heat capacity of water, because that's one of the common ones that comes up. So they're asking you how much energy is needed to heat 2 kilograms of water from 10 degrees to 100. So best practice is to write out the equation. So write it out in words. Energy, or change in energy here, is equal to the mass times the specific heat capacity times the temperature change. So go through each part of the equation. So the first bit here, energy, that's what they're asking you to find out. So write that down. Question mark, we don't know it yet. The mass, they're giving you that here, 2 kilograms of water. One thing to remember about this is the unit of mass is kilograms. So if you get it given to you in grams, you need to convert it to kilograms. C for specific heat capacity, which you are given 4,200. The last part of the equation is the temperature change, delta theta. And you work that out. It says that the water rises from 10 degrees to 100. So you take those away, so your temperature rise is 90. Now in an exam, you will more than likely get a mark for just doing this part of the calculation, working out the temperature change. So the right hand side now in red is giving you the worked example, the equation there written with symbols, and then everything substituted in, and here is your answer here, the change in energy, the amount of energy needed, and the unit of energy, very important, joules, always written with a capital J. If you're asked to give your answer in kilojoules, just remember there are 1,000 joules in 1 kilojoule. Okay. You probably won't have to do this for Trilogy. However, just in case, it's worth having a go at seeing if you can rearrange the equation to find C, or they might ask you to find the mass, or even the temperature change. So if you want to pause the slide a minute and have a look at how would you make C the subject of the equation. Okay, so here is the equation rearranged. So how did we get from here to here? Basically, you need to get rid of mass and delta theta temperature change. So you divide this side by mass and temperature change, but whatever you do to this side, you have to do the same to this side of the equation. And all I've done here is just swapped it over to the other side so that C is written on the left hand side and energy on the right. But you have the mass and the temperature change cancelling out on that side, and on this side you get remaining energy divided by mass multiplied by the temperature change. Now, why would you need to know about specific heat capacity? Well, different materials have different values of specific heat capacity. So a high value like water means that that material can store a large amount of heat energy for a smaller temperature change. So for example, radiators use water because it's got a very high specific heat capacity. You can get oil in radiators, but usually it is water. In reverse, materials with low specific heat capacity tend to be metals. So that means that they don't need much heat energy to raise the temperature. And so, for example, pans, saucepans are made of metal. So this slide has got some questions for you to have a go at, and the next slide is for green penning the answers. There's a bit more of an accurate value for water specific heat capacity here, and like I said previously, you won't need to know these values. They will give them to you if you're needed to substitute it into an equation. So the final part of the lesson, if you have a go at these equations, and then you can green pen them. So here's the slide that you can use for green penning your answers, correcting your answers in your book.